Okay, so this video will be part B, B1 and B2, of the June 2017 Regents exam. So let's begin at the beginning and restart with an estimation question. They love to start there, so let's start there. So the first thing you should do with estimation is write out the numbers so that they look like numbers and not just exponents like powers of 10. Okay, so we have 0.01 meters, which is a centimeter. That is not a kitchen table. We have 1 meter, that could be. We have 10 meters, not a kitchen table. 100 meters, not a kitchen table. Choice 2. I think that one was pretty clear. Some of them are ridiculously easy. Some of them are pretty tricky, but I thought that one was doable. Next. Ball's thrown 35 meters per second at 30 degrees. What has a magnitude of 0 when it's the highest point of its trajectory? Trajectory. Wow, say that 5 times fast. Anyway, please don't say the acceleration is 0. Everybody wants to say that. That is not true. The whole time, the acceleration, even at the highest point, is straight down at negative 9.81 meters per second squared. So it is not the acceleration that is 0 at the highest point. And then momentum of the ball, momentum is mv. And you might be like, oh, it stops at the highest point. It stops vertically at the highest point, but there's still forward velocity that remains true, constant forward speed the entire time. It does have momentum at the highest point. If it didn't have momentum at the highest point, that would mean it straight up stops and it's thrown at an angle of 30 degrees. So it does stop for an instant in time if you throw it straight up, but if you're throwing it at an angle, it will have some velocity the entire time. So if it has velocity, it has momentum, so it's not momentum. Horizontal component, no, because the forward speed remains constant. That horizontal component is going to be 35 cosine, the x velocity is 35 meters per second cosine 30 degrees, which I'm not going to even do that on my calculator, but I can tell you it ain't 0, so it will have horizontal velocity the entire time. But you know what is 0 at the highest point for an instant in time, for instantaneous time, is the vertical components of the ball's velocity up at the highest point. Alrighty, so that is 37. 38, I have a velocity versus time graph, and I know that with it even looking at the question, I know that the slope of v versus t is acceleration, and the area under the curve, which is shaded, so they're probably going to ask me about it, that is displacement. Alright, so let's see, graph below represents velocity versus time. Yes, I can see that. Shaded area under the line represents the displacement. We just said that. There's a mnemonic for this. I don't know if that mnemonic is any good. Let's see. We have displacement, velocity, acceleration. And then displacement is the area under the v versus t graph. And then velocity, change in velocity really, is the area under an acceleration graph. We don't really see that often. And then going the other way, acceleration is the slope of v versus t, and then velocity is the slope of d versus t. Even if that mnemonic is not helpful with graphs, when you go on to take calculus, that relationship in terms of area under and slope of between displacement, velocity, and acceleration, that you're going to come back to that and be like, oh, so that's what Hessel was talking about. I mean, once you take calculus, that'll become more clear. Anyway, calculus is not on the Regents exam, so shut up about calculus. 39. Spring stores 10 joules of potential energy compressed 0.2 meters. What is the spring constant of the spring? So spring potential energy is what it's talking about here. Elastic potential, by the way, that means spring. So if you're like, what the heck is elastic potential energy? It's spring potential energy. It's 1/2 k x squared. So I'm going to put in 10 joules on the energy. I'm solving for k. I have the compression as 0.2 meters. Do not forget to square that. And so k, when you go to solve for k, 0.2 squared is 0.04. Half of 0.04 is 0.02. Divide both sides by that, and we get 500 newtons per meter, and that's choice 4. Newtons per meter is one of the most forgettable units in the class because it's only used for spring constant. Thankfully, we didn't need to remember it because all of our answers have those units for us. So that's the first column there. Let's move on to the next column. We have 40 and 41 based on this cannonball. 1 kilogram fired horizontally from 500 kilogram cannon, initially at rest. Horizontal friction on the surface. Cannonball acted on by an average force of 8,000 newtons for 1 times 10 to the negative 1 seconds. What's the change in momentum? So let's write down things that I know. We know the mass of the cannonball. Maybe we'll call that M1 is 1 kilogram. And we know M2 for the cannon is 500 kilograms. And sometimes it helps if we draw a picture. We have a cannon and we have a cannonball. And so the cannonball gets fired. And this would be M2 for our cannon and M1 for our cannonball. And so the 500 kilogram cannon is initially at rest. The whole system is initially at rest. So I guess I can say total momentum before equals 0. This is going to be an explosion problem. I don't know if that has a bearing. It does not have a bearing on number 40, but like questions like this, it's worth noting that. So then cannonball is acted on by a force. So the net force on the cannonball is 8,000 newtons. And the time that it acts for is 1 times 10 to the negative 1 seconds. And it says, what's the change in momentum? So I know that change in momentum is F net T. And I know the net force is 8,000 newtons. And I know the time is 0.01 seconds. And so that's 800 Newton seconds or 800 kilogram meters per second. And so that's going to be choice 2. And then 41, what is the net force acting on the cannon? It is equal to the force on the cannonball. The force of A on B is equal to negative the force of B on A. And this is why cannons are usually mounted on wheels, because the cannon rolls backwards after it fires the cannonball. Cannonball goes screaming across the field, but the cannon does roll backwards because if there's 8,000 newtons on the cannonball, there's 8,000 newtons on the cannon too. And the cannon weighs way more than the cannonball, so the cannonball accelerates way more than the cannon does, but the cannon still moves because there's the same amount of force on it because of Newton's third law. All right, so we have 8,000 newtons on both of them. That is choice 3. All right, 42, metal sphere X, initial net charge, negative 6 times 10 to the negative 6 coulombs. A second sphere Y has positive 2 times 10 to the negative 6. They touch each other and separate. What's the charge on X after they touch? So this is charge by contact, otherwise known as charge by conduction. And so when you have two things touch that are charged, the charges even out, so they have the same electric field strength on both, so they stop sharing charges. So if the charges even out, what does that even mean? We have to average the charges. How do we do that? If we have two objects, we add them up and divide by 2. So we have negative 6 times 10 to the negative 6 coulombs, and we have plus 2 times 10 to the negative 6 coulombs. And if we average those together, divided by 2, that gets me negative 2 times 10 to the negative 6 coulombs, and that is choice 2. All right, next question, 43. Force of 70 newtons applied to 20 kilogram crate moving towards the east. Friction force is 10 newtons. What's the crate's acceleration? All right, so things that I know. Now, friction force is 10 newtons. I'm going to put that in as west because friction opposes motion. So if I'm saying that the 70 newtons east is positive 70, I'm going to say that my friction force is negative 10 newtons. That's going to matter in a second. It wants to know the acceleration. Delta V over T would be nice for acceleration if I knew velocities and time. I know none of that. So the alternative is Newton's second law, F net over m. Well, I have the mass, and my net force is 70. Oh, but wait, it is not 70 because we have friction, right? So remember our, what I like to call the backup friction formula, push minus friction. I know the push and I know the friction. So I have 70 newtons minus, we say plus negative, but minus the friction force is 60 newtons for the net force. I'm putting in 70, but 10 is acting against me, so my net is 60. So when I go for my acceleration, 60 newtons over 20 kilograms, that's pretty much 6 over 2, which is 3 meters per second squared, and that's going to be choice 3. All right, that's that column. Next page. How many pages in total? 3 pages. We can do it. Let's go. 44. Relationship between energy and wavelength of a photon. My formula is hc over lambda. Energy and wavelength are inversely proportional. Energy and frequency are directly proportional, but energy and wavelength are inversely proportional. Anything that is inversely proportional looks like that curve, that hyperbolic curve of y equals a constant over x. So that is choice 4. Groovy. 45 and 46. We have a spring that a guy is a person. I shouldn't gender the stick figure, right? A person is vibrating on the wall, and it looks to me like a standing wave. So it says student vibrates the other end of the spring wave that moves to the wall and reflects back towards the student, making a standing wave because is the best way to make a standing wave. That's kind of like when I took the rope spring and I shook the rope spring when it was attached to the desk to make a standing wave. Same principle. All right, 45. Phase difference between incident reflected wave at point P. Point P is a node. That's maximum destructive interference. I know it's a node because it's the waves are canceling at that point. Node, 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 node. There are 4 nodes there. All right, so it's max destructive interference. Then you have to realize what the phase difference is for maximum destructive interference. Crests are meeting troughs, and that happens at 180 degrees apart. So that is choice 3. 4. Total number of antinodes in the standing wave. Well, the antinodes are in between the nodes. I got 1, 2, 3 antinodes, and that's antinodes are points of maximum constructive interference. Max constructive interference. And that's where you get the most motion, and that's happening in 3 spots on that wave. There are 3 antinodes in that diagram. All right. Then 47, we get this nice big picture of some wires. It's relating length and area of a conductor. I know right off the bat the formula that I'm interested in is resistivity times length over the area for resistance. And it says they're all at 20 degrees Celsius. That is room temp. So that is the temperature for the resistivity chart on page, what page? 4? 4 of the reference tables. All right, which one has the greatest resistance? So which one has the biggest R? So I want to have a big length. I want it nice and long, but I want it to be thin. I do not want cross-sectional area because resistance and area are inversely proportional. The bigger the area is, the less the resistance. So I want a thin wire. I do not want a thick wire. Thin wire, and I want it to be long. The longer it is, the bigger the resistance. So long and thin is going to give me a big resistance. That is wire 2. All right, that page is done. And then we're on to this page. And I am missing... Oh, wait. There is B2. All right, so for a second I was like, wait a minute, I forgot the B2. No, the B2 is down here. We'll get back to that. Anyway, 48. 48 and 49 in the diagram below. Two charged identical metal spheres. What is the excess elementary charges on A? I know the charge in coulombs. I'm going to convert that to elementary charges. So I have 4 times 10 to the negative 6 coulombs. And I know that my conversion from page 1 of the reference table is that 1 elementary charge is 1.6 times 10 to the negative 19 coulombs. That, again, page 1 ref tabs. And so I'm going to divide here. And when I work it out, I get 2.5 times 10 to the 13 elementary charges, choice 3. Then 49 says, what is the electric force between the two spheres? My electrostatic force is K Q1 Q2 over R squared. So let me give myself a little bit more room. The electrostatic constant K, 8.99 times 10 to the 9 Newton meters squared over Coulomb squared. And then my two charges are, let's see, this is magnitude, so I don't really care about the positive or negative, just the amount. 4e6, 3e6. 4e negative 6, I should say, coulombs. And 3, 4, and 3, yes. 3 times 10 to the negative 6 coulombs. And then my separation between them is 2 meters. And after all that, do not forget to square the bottom. Now in your calc, I would do the alpha y equals to put this into fraction mode. And also use the E, but 8.99 E9, that's second comma on your calculator. E. Second comma on the calculator. We get 0.027 newtons, which would be 2.7 times 10 to the negative 2 newtons for 49. And then the last multiple choice question on the 2017 Regents exam. This looks like Doppler effect to me with the nested circles. And it says the source is moving towards the right. And it says compared to wave frequency observed at A, the wave observed at B. B has a higher frequency as the waves are bunching up. It is a higher frequency and it is a shorter wavelength. Moving away from A observes a lower frequency and a longer wavelength because of the Doppler effect. So compared to A, B has a higher frequency and a shorter wavelength. So that's choice 1. With these questions, one thing, be very careful reading when you're doing these comparison guys, because you could totally understand the physics and the principles and then just get it backwards. Like, be like, oh, like, A as compared to B. No. This question's saying B as compared to A. But you can see how if you get that backwards, you would totally get it wrong, even though you understood the physics. So, you know, the number one thing we find that kids do wrong on Regents exams is that they don't read carefully. Right? So be careful. All right, so that is the multiple choice. Now we move on to the B2s, which is extended response. You would do the B2 in your answer booklet. I don't have the answer booklet here, so I'm going to do it on the answer sheet. I can because I can pinch to zoom. You can't do that on regular paper. If you can, you're like a wizard. Anyway, 51 to 65, record your answers in the answer booklet. I just said that. Thank you very much. 51, sketch at least 4 magnetic field lines of force around a bar magnet. I have my handy dandy answer key that I'm looking at here on my computer, and I'm scrolling down to 51, and it's a bar magnet with the south on the left end. So that would have south, whamp, south, north. Field lines are closed loops. Closed loops says at least 4. 1, 2, 3, 4. Try not to cross them. And the direction, we need to include the direction, and it goes from north to south. So out of north, well, it looks like I crossed some lines a little bit. And then in to south. There it is. That's the answer to number 51. Include arrows to show direction. I think that should be 2 points, one for the shape, one for the direction, but nobody asked me. All right, 52 through 54. Tritium. Oh, look, it's a wordy question with a big paragraph. I bet it's a standard model question. They love to do that. Tritium is a radioactive form of element hydrogen. Tritium nucleus is composed of 1 proton and 2 neutrons. This was on the test you guys just took. 1 proton, 2 neutrons. Tritium nucleus decays, emits a beta particle, which is an electron, and an antineutrino to create a stable form of helium. During beta decay, a neutron is spontaneously transformed into a proton, an electron, and an antineutrino. How many quarks in a tritium nucleus? We have a proton. We have 2 neutrons. So the proton, you should know, is up, up, down in terms of its quarks, and the neutron is up, down, down. You don't need to know that fact to answer this question. You do need to know that these guys are baryons, and as baryons, they have 3 quarks apiece. So when you had all of those together, 3, 3, and 3, 3 quarks, 3 quarks, 3 quarks, 9 quarks. Notice they're not asking for the charge, they're asking for the number of quarks. So that is 9 quarks. 53, total charge of a proton, an electron, and an antineutrino. So of all of them, the total charge together. Proton is plus 1e. The electron is minus 1e. And then the neutrino, the antineutrino, is neutral. Neutrino is neutral. Anti of neutral. Anti means opposite charge sign. Opposite charge sign. But the opposite of neutral is neutral. So we have plus 1e and negative 1e, and 0 gets me 0 elementary charges. There is no charge altogether. So the combined charge of a proton, electron, and antineutrino is nothing. Because while the proton and the electron are charged, one's positive, one's negative, they cancel each other out. 54, fundamental interaction responsible for binding together the protons and neutrons in the nucleus. Now be careful, this whole question is about beta decay, and beta decay is about the nuclear weak force. But that's not what they asked. They said, what is the binding together the protons and neutrons in the helium nucleus, holding the nucleus together? That would be the nuclear strong force, because the neutrons don't normally react with each other. They're neutral, except when you get them real close. And then the nuclear strong force holds them together. Nuclear strong force also opposes the natural opposition of protons they have towards each other. So that's a nuclear strong force 454. All right, how many pages do we have here? Okay. That is 52 to 54. Next question, we have projectile, horizontal projectile, and it says 10 meters per second, lands at time t and distance d from the base of the cliff. Second ball projected horizontally at twice as fast, 20 meters per second. And it says determine the distance the ball lands from the base of the cliff in terms of d. So this is a horizontal projectile, and it goes twice as fast. So we're talking about distance here. So the x distance is the x velocity times the time plus 1/2 axt squared. There is no x acceleration. So really we're just dealing with that the range is the x velocity times the time. We have not changed. It's going to be the same time because it's the same y information. It's the same height. It's an initial, the initial y velocity is 0 because it's a horizontal projectile. Nothing has changed vertically, so it's going to be the same time. So the time is going to be the same. But my speed is twice as much. I'm going twice as fast because I'm going 20 meters per second instead of 10 meters per second. So with twice as much speed, I'm going to get twice as much distance. So in terms of d, how far is it going to go? With new speed at 20 meters per second, it's going to go twice as far. 2d for 55. You could set up a table for horizontal projectiles. You don't really need to answer this question. But you do need to realize that the time remains the same. So it's the same time, but throwing it twice as fast forward means it's going to go twice as far. So that's 55. All right. Then we have 56, 57 is its own question by itself. And again, the 2-point questions have 2 question numbers. So that is a current, I know the current of 0.71 amps connected to 120 volts. And it says how much time if you have an energy, which electrical energy we know as work, that's 3 times 10 to the 5 joules, and it wants to know the time. So I do, let's see, I know the energy, but I don't know the power, so I can do this all in one shot with W equals V, I, T, and I'm going to solve for T. So I get 3 times 10 to the 5. That's 300,000 is equal to 120 times 0.71 times T. Solve for T. I'm not giving myself much room, so I will cheat, and I will zoom. So T is equal to 300,000 over 120 times 0.71. And so that time, 3,500 seconds. I cut it down to 2 significant figures because my current is 2 sig figs. So 3,500 seconds when you work it out in the end. All right, so 58:59. I'm so close to done with this B2, but I have to pause at this point. I will come back to this. So 58:59, I don't have a centimeter grid, so I'm going to make a centimeter grid here. But it said amplitude of 2, wavelength of 6. So I copied the grid from the answer book. And so this guy here, we have 2 centimeters of amplitude and 6 centimeters of wavelength. The one cycle needs to complete in 6 centimeters. It only says 1 cycle, so that's all that I drew. 60 is by itself. All right, so for 60, they give the force on the spring. It's a 35 Newton weight, so that's the force on the spring is 35 Newtons. And the stretch is 0.1 meters because it started at 0.15 and it stretched out to a full length of 0.25. If you remember our Hooke's Law lab, we had to do this. We had to subtract out the rest length of the spring. So spring constant, we have F equals Kx, we're solving for K. So X is 0.1, not 0.25. And so we do 35 divided by 0.1, which is 350. There goes the bell. And the units would be newtons over meters, because if F equals Kx, K is F over X, newtons over meters. And so that is our answer. 61, how much mass in kilograms gives 1 gigajoule? So gigajoule, that's a billion joules. And you get, that's page 1 of the ref tabs to get those prefixes for powers of 10. So we have how much mass is 1 times 10 to the 9 joules. Well, E equals mc squared. I do 1 times 10 to the 9 joules is m times c squared. Speed of light in vacuum, page 1 of the reference tables. So if I divide the 3 times 10 to the 8 squared by both sides, I get a mass of... All right, we have 62, the difference between thunder and lightning. And this question is a little wordy, but don't overthink it. Thunder is sound, and the lightning is seen. I need my pen. Lightning is seen, and then thunder is heard. So seen is light, and heard is sound. Speed of light is 300 million meters per second. Speed of sound at STP, even not at STP, even at like, I don't know, 70 degrees or something. V of sound at STP is 331, 3e2 meters per second. Like, the speed of light is literally 1,000,000 times faster than the speed of sound. So that is why lightning is seen before thunder is heard, because light is ridiculously faster than sound is. So V of light is way bigger than the speed of sound in any medium. All right, 63, 64. Bolt of lightning transfers 28 coulombs of charge. Q is 28 coulombs through an electric potential difference of 3.2 times 10 to the 7 volts. And then the time is 1.5 times 10 to the negative 3 seconds. And it says, what is the current during this time? Well, I don't need the voltage. If I want to know what current is, it's Q over T, which is 28 coulombs over 1.5 times 10 to the negative 3 seconds, which is, and we get a lot of current, 1.9 times 10 to the 4 amps. It's a lightning strike. It's a lot of current. What do you want? And then our last part B question is number 65, and we have the two square pulses. One has an amplitude of 1 meter, and then the other one has an amplitude of negative 0.4 meters. And so when we put the two of them together, the negative 0.4 knocks down the 1 meter. And so we have 1 meter minus 0.4 meters, and that gets us positive 0.6 meters. And so the pulse in the middle for AB is still going to be up, but it's going to have an amplitude of 0.6 meters. And that's my pulse. Now, you would do that in your answer booklet, but I'm kind of doing it on this grid instead. And that's that. So that's part B from June 2017. Stay tuned for part C.